everything I say in this seminar is joined with Rina Anno from Kansas, my long-term collaborator. Just a moment, let me set up. Yes. So the plan of this talk is that first I will tell you about sort of the standard notion of bounded twisted complexes, which was invented by Alexei Bondal and Mikhail Kapranov in 1990s. And then I will talk about how to generalize them to unbounded case. But everything in this talk is not only joined with Rina Anno, but owes huge intellectual debt to the work of Alexei and Mikhail. So throughout this talk, let's set up some notation. Mod K is the monoidal category of complexes of vector spaces over a field. It is enhanced over itself, meaning, of course, home space between two complexes of vector spaces is itself a complex of vector space. So A will be initially small, differentially graded DG category. And DG category just means that our category is enhanced over mod K. The home complexes are complexes of vector spaces with all the usual sort of formality of being enhanced over something. Given a DG category, a category whose home complexes are complexes of vector spaces, we can take its homotopy category. This means truncating every home complex to its zeroth cohomology. That will give you just an ordinary category. And another important player is the category mod A, the category of right DGA modules. Formally, it is defined a right DGA module is a DG functor from the opposite category of A to complexes of vector spaces. So effectively, for every object of A, we've got a complex of vector spaces, and therefore every morphism of A acts on these vector spaces by sending them to each other. So in a sense, one can think of a DGA module as essentially a complex of vector spaces with A action. And this complex of vector spaces has extra grading, bi-grading by the objects of A. So know that I will sort of try to not to pay too much attention to set theoretical issues, but to do this, you really need for your category A to be small, meaning its objects need to form a set. Because if you don't do this, the home spaces of this category will not lie in mod K. Because in mod K, the objects are complexes of vector spaces, which are sets. So usually, if you have a small category, then you have a luxury of working with mod A. If your category is not small, you can still work with mod A. But first, you have to enlarge your universe in a way which makes A essentially small. Then, large universe, you can work with mod A. There is necessity for doing that, and we'll talk about a bit more about this in the unbounded case. So, what are usual bounded twisted complexes? Well, a twisted complex over a DG category is the following set of data. It consists of, for every integer, an object of AI indexed by that integer. And we want our complex to be bounded. So we want these objects to be non-zero only for a finite number of indices. So it's a finite collection of objects of A, Z graded. And then for any pair of integers, you got a morphism and morphism, of course, in our DG category A of degree I minus j plus 1 from AI to AJ. I will give an example of all of this. And this data must satisfy the following condition, often known as twisted complex condition. If you take any ij and differentiate in DG category. I mean, A is the DG category, so we can take any morphism in A and differentiate it and obtain a morphism degree 1 higher. So if you do this to any of these alpha ij's, which are called twisted differentials, that will be precisely the sum of all twisted differentials starting at I, going to any other existing object K, and then coming back from that to J via another differential. This is called twisted complex condition, and I will illustrate it in a second. A twisted complex is called one-sided, and in all honesty, I would say that as I will explain shortly, Alexei and Mikhail were mostly interested in one-sided complexes. If you know twisted differentials going from higher indices to lower indices. So all the arrows in your, all the differentials go from left to right. So here's an example of a twisted complex on 5 objects. So we have objects A0, A1, A2, A3, A4. You've got, these are differentials. These are differentials degree 0. Blue are differentials of degree -1. Purple of degree -2, and pink here of degree -3. And if you look in a one-sided, now if you've got a twisted complex which is not one-sided, you've got a structure exactly like this, but going in the opposite direction here. So just mirror reflect this, and you will get the sort of the full twisted complex. But for one-sided twisted complex, if you look at what the twisted complex condition means, it tells you first that these guys are closed morphisms because there is no other way. You cannot go from A3 anywhere and come back to A4 because you've got no sort of arrows going backwards, or you cannot go here and go back here. So the twisted complex condition in case of these guys just tells you that they're closed. In case of, say, alpha 1, 3, the twisted complex condition tells you that the differential of this is the composition of these two guys. And that tells you that in the homotopy category, the composition of these two guys is 0, because in the homotopy category, every boundary dies. So this higher differential means that you are asking for your sort of ordinary differentials from between the consecutive objects to be morphisms in the homotopy category. And now you are fixing homotopies up to which the composition of any two subsequent ordinary differentials is 0. And then say alpha 0, 3, the differential of that equals to the sum of doing this and then doing this higher homotopy, doing this ordinary guy and doing this higher homotopy. So as usual, once you've introduced the higher homotopies, so if you view, so this can be viewed as a lift of a complex of objects from the homotopy category up into the DG world. And once you introduce the homotopies which control the condition that the composition of any two subsequent guys is 0, you then have to introduce higher homotopies which control the interaction of these homotopies and their regional morphisms, and so on. So this is what a single twisted complex is. We can make twisted complexes into a DG category by defining this in the following way. A Hom complex between two twisted complexes, AI alpha ij and BI beta ij, looks like this. You simply take all possible, this direct sum here tells you that you take a finite collection of all morphisms from AI to BJ and of degree k. And a morphism of degree k from some AI to some bj will have degree k plus j minus I in this complex. So as a graded vector space, it is this. And then to define a Hom complex, I need to take this graded vector space and define a differential in it. And differential is given by this formula. Again, one should read this formula as that if you have any morphism F from AI to BJ. You to differentiate it, you differentiate F, and then you also do kind of the usual thing. You also compose F, post-compose F with all the differentials at the target complex, and pre-compose F with all the differentials in the source complex. So, and then we usually call the full subcategory of the digit category of twisted complexes, which consists of one-sided twisted complexes, as Prater A. And I will explain the reason for that name in a moment. So this is a lot of data. We're essentially saying we've got a finite collection of objects AI, finite collections of objects BJ. We take, here's an example, really all possible arrows from every object of this complex to every object of this complex. Prescribe degree and impose no conditions on them, but impose this differential. Now, the differential it is interesting to look at what this differential tells you for the morphisms of degree 0, because then the closed condition means that you obtain a genuine morphism in the homotopy category, which is. And so just to give you some intuition for how this works, let's look at this example. Here we have two twisted complexes of length 3. And here I've written literally the data of all the components of a morphism between them. I call F morphism consisting of all these components. And again, black are degree 0, blue are degree -1, purple is degree -2, but now we also have degree +1 and degree +2. And if you look at what happens, firstly, so for example, suppose we differentiate, what happens when we start differentiating F? Well, if you differentiate F and look at the component 1, 1, you will have this differential of F11, but you will also have composition of alpha with FO2 and composition of F10 with beta 01. And what this tells you is the following. If your morphism is closed, then this tells you that F11 has to either be closed, and if it's closed, you can just have this guy's B0, or its differential is 0 up to homotopy, because these two guys give you a homotopy between two complexes, up to which this is 0. And again, it's educational to look at what happens, for example, when you look at this degree -1 components. The differential of F12 is precisely the commutator of this square and sort of this extra homotopy. So if there are no green guys involved, you're really talking about you will start seeing morphism of complexes. These guys will be closed. These guys, this square will commute up to this homotopy, and then these sort of two homotopies will commute up to with these guys up to this homotopy, and so on. But and in many natural constructions, you can get away without these guys. But having this degree, positive degree homotopies, also gives you freedom of dealing with morphisms here, which are not closed, but only closed up to homotopy. So now the real explanation behind this definition, for example, for where this is what if you look at this picture, you can get some intuition for where this formula comes from. But the real explanation for this is that we can define a convolution functor, which takes you any twisted complex and gives you a single A module. And the way we do it is we take a twisted complex, and then in the category of mod A, we have, this is a category of A modules. So this is essentially complexes of vector spaces with a sort of grading by A. So we have operations such as a shift, and we can take infinite direct sums. So I can take AI, which is an object in A, but I can consider it via the standard Yoneda embedding as a representable module inside mod A. I can take a direct sum of AIs, well, these representable modules, with shifts, and then I cook up a new differential. So I take this as a graded module. I take its natural differential d old, and I add to it all the twisted differentials. The degree condition on this is precisely, the fact that this is degree 0, this is degree -1, this is degree -2, and so on, ensures precisely that the sum of all these differentials become degree 1 when you consider them as morphisms from this shifted collection of AIs to themselves. And the twisted complex condition, this guy in the definition of twisted complex, is precisely equivalent to this new guy being a differential, meaning the square of it being 0. And then let's look at the morphisms. This is where sort of things really become clear. So we look at the home in the category of twisted complexes of A between these two guys. Well, we define this above here as this collection of all possible morphisms from all AIs to all BJs with sort of prescribed degree shift. So here is the sort of crucial point. There is an obvious, forget about differential, the funny differential we defined here. Forget about the differential over here depends on the two new differentials we've defined. The twisted differentials on this twisted complex modify the differential here, twist differential on this complex modify differentials here. But if you forget about differentials and consider these as just graded vector spaces, they're isomorphic in an obvious way. You just sort of bring out all the shifts. And since this is only a finite collection of objects, you can also bring all the direct sums outside. So the statement is that the obvious graded vector space isomorphism between the left-hand side and right-hand side. So this funny differential, the new differential we defined on this graded vector space, is simply the image of the natural differential here, which means we consider this guy with a new differential, we consider this guy with a new differential. We have two complexes of vector spaces here, so there is a natural home complex of vector spaces between them, and that defines a natural differential here in terms of these guys, and then its image under the isomorphism is precisely the thing that was used to define the differential in the category of twisted complexes. So the whole thing was basically set up. The very definition of the category of twisted complexes is just equivalent to saying that we've got a fully faithful subcategory of mod A supported on DG modules whose underlying graded module is the shifted sum of objects of A. And in a sense, the definition of a twisted complex is simply a nice way to keep track of the data of such module, of the data of the module itself, which means the new differential, which you modify the natural differential in this graded module, and the data of morphism between two such guys, where the most interesting thing is how you differentiate such morphisms. So basically, this will become important for the unbounded story. So more or less, once you have prescribed, once you've decided what corresponds to your collection of objects AI, once you've said that what corresponds to them is this direct sum with shifts, everything else is just immediately fully determined by this requirement. So my goal is to finish summarizing bounded twisted complexes in first half of the talk, and I think I'm on track to that. For that, so I can afford to tell you the sort of the really cool part of the story of bounded twisted complex, and that is why is Pretra A called Pretra A, and why are people interested in one-sided twisted complexes? Well, the reason is that homotopy category of the category of A modules has a natural triangulated category structure. This is because the A modules are just complexes of vector spaces with an extra grading. So any category of complexes of vector spaces up to homotopy has a natural triangulated structure. This is sort of the triangulated structure that sort of led to definition of triangulated categories. So basically, the H0 of mod K has the original triangulated structure on it, and then we can simply define it for A modules level wise for each. If you want to define a cone of morphism of two A modules, you just do it for each object of A. You consider the cone of the corresponding morphism of complex vector spaces. So with that triangulated category structure in mind, the convolution of two-step twisted complex. And what's a twisted complex on two objects? Just two objects and degree zero morphism between them. Well, by the definition we have here, we take B and A shifted by one. This is in degree -1 position, so it's ended up being shifted by one. We take the natural differential on this as sort of under unit. So this is a complex of vector spaces. This is a complex of vector spaces. They have an internal differential. And we modify this by F, which becomes a morphism sort of from A into B of degree 1. This is precisely the definition of what cone of F is in the category of A modules. Once you embed these two guys as A modules, make them to complex vector spaces, then this is just a cone. And then if you look at the complex, at the morphism of let's look at a morphism of twisted complexes of this form. 2 degree 0 morphisms and degree -1 morphisms here, which is closed of degree 0. Well, what you will have is you will have this extra data, this extra degree -1 homotopy up to which these two guys commute in homotopy category will determine this complex convolves to a cone of F. This complex convolves to the cone of G, and this morphism of twisted complexes convolves precisely into morphism from cone F to cone G, which completes this to a morphism of exact triangles. So this is why cone is not functorial. This is where all that nonsense comes from, because there is more than one possible homotopy up to which the square can commute. So sort of one shouldn't ever try to sort of come up with a proper functorial cone because there is intrinsic reason for cones being non-functorial. And finally, a very interesting thing is to look at what's a convolution of a two-step complex. So suppose we have a twisted complex on 3 objects, 2 morphisms of degree 0, 1 degree -1 morphism whose differential is the composition of these guys. Well, what happens is take this complex and then take cone of F. So take an exact triangle like this. Then the data of H determines a unique lift, which allows you to take this cone and sort of replace the objects A and B and morphism F between them in the original complex by the cone of F. And then we can take another cone of this lift. And what we'll get is the convolution. So convolution is an iterated cone. We replace A to B by F by cone of F, lift G to a morphism from cone of F to C, and then take another cone. This is called the Postnikov system. And in fact, this is called the left Postnikov system because there is also a right Postnikov system. You can do the same thing to G. And if you're just stuck in homotopy, in triangulated category, there is no reason for this lift to exist. There is no reason for it to be unique. And there is certainly no reason for there being always if you manage to do this and manage to get some convolution, there's no reason for you to be able to arrive to the same convolution if you start by replacing these guys by the cone of G. So, but if you've got a twisted complex, that automatically allows you to start replacing any two objects by the cone of morphism between them, and then keep doing this until there's only one complex object left. So roughly, the data of one-sided twisted complex over A is the complex of objects in homotopy category, plus the higher data which specifies all possible Postnikov systems, all of them giving the same convolution. So all possible ways to take iterated cone of this guy. And the precise statement, of course, what does it mean that we take all pre-triangulated, all one-sided twisted complexes over A? That means that we add to objects of A all things which can be obtained from objects of A by iterated cones. And the precise statement, of course, that yes, the homotopy category of Pretra A is exactly the triangulated hull of A in the triangulated category mod A. Notice that this is not triangulated. This is not obliged to be triangulated at all for an arbitrary DG category, but this is always triangulated. So you take these guys and you complete them to triangulated category inside here. And this is what this procedure does on DG level. So Pretra A is called like this because it is the pre-triangulated hull of A in mod A. So this sort of finishes summary of classical sort of theory of twisted complexes due to Alexei Bondal and Mikhail Kapranov. Before I start on unbounded twisted complexes, are there any questions? Can I just check that my Zoom didn't freeze and that you guys are hearing me? So can somebody sort of confirm that?
Everything's perfect.
Perfect. Sorry. I've given undergraduate lectures where I talked for 30 minutes and then I was informed that the Zoom had froze up. So I always try to check up on this. Excellent. So what happens with unbounded twisted complexes? Well, let's take a small DG category over K. What if you want to work with unbounded complexes over A? Well, there is a naive definition, which means let's just do the same thing. I mean, never mind that this is now not a finite direct sum. You can still, basically, we still want to arrive at the same answer. We want to have a fully faithful convolution functor, which will send any twisted complex to now infinite direct sum in mod A, and mod A is a big category. It has all infinite direct sums with these guys modifying a differential. So if you follow your nose, you will arrive at the definition of an absolute unbounded twisted complex. Why the word absolute? I'll explain this in a second. So it's essentially the same definition. I've highlighted the differences in blue. And another difference is we no longer require the number of objects to be finite. But this comes at a price that we now have to impose a finiteness condition on morphisms. So you now have a fully sort of Z-graded collection of objects of A. You have morphisms going between them with prescribed degree. And this I still should add this here. So the new condition is for every object AI, there is only finite number of twisted differentials emerging from it. This is the precisely condition that you need for the sum of these guys to give an endomorphism of this direct sum of shifted copies of A. I mean, what do you need to have a morphism from direct sum to direct sum? Well, from any one object here, you shouldn't go to an infinite number of objects because then the image will not belong to the target direct sum. And the same old twisted complex condition. So then you define DG category of absolute unbounded twisted complexes in the same way you define a Hom complex in this. Plus minus means unbounded in both directions. We introduce this notation because we also use notation TW plus for bounded above, TW minus for bounded below, and just a moment. No, I think I want, sorry, TW plus for bounded below, TW minus for bounded above. So we used to have This home complex being just a direct sum, a finite number of arrows going from AI to BJ with prescribed degrees. Now, instead of having a finite number of arrows, we allow infinite number of arrows with exactly the same condition. This product here means that you're allowed to have a finite number of arrows. So this is a direct sum. So for every object AI, you have a finite collection of arrows going to various objects BJ. And then you still need this to be a direct sum over in each degree. You must have. I mean, we still want to end up in the DG category more days, so we do not allow infinite number of components, of degree components. And the amazing differential is defined by exactly the same formula. So to differentiate any component, any arrow from AI to BJ, you differentiate it in exactly the same way. Differentiate it and then add to it all the sort of paths in your twisted complex which go between the same arrows via some twisted differentials and other components. So this gives you a fully faithful convolution functor from the category of absolute twisted complexes into category of mod A. So, that seems to be the end of the story. Why would you ever want anything else? Well, firstly, because if you've ever worked with sort of bar constructions of algebras and coalgebras, this allows you to have a bar construction of an algebra, but not a bar construction of coalgebra. Secondly, this really, when you start thinking about it, is not always the best definition. So here's an example which, in a sense, motivated us, and with which I hope to convince you that sometimes it's worth not using this definition. So suppose A is closed under countable direct sums and shifts. For example, A is a category of modules over DG modules over DG category C taken in a smaller universe. I will want to talk about mod A, so I cannot just say A is a category of modules over some small category C. I have to say that A is a category of modules over small category C taken in a universe one cardinality lower, so that this is a small category in the current universe. Alternatively, take a small category C, take a category of modules over it, and then enlarge your universe to make it small. Or, but these are sort of drastic measures. All I'm asking is for A to be closed under countable direct sums, not all small direct sums. So the crucial, important issue here is that if you already have direct sums, countable direct sums, integer sort of graded direct sums in your category A, then the Yoneda embedding does not respect those. It does not commute with infinite direct sums. So if you take a direct sum of the Yoneda embeddings of a collection of objects AI and A, then what you have is this direct sum of homes of these representable modules, homes from in A from something, some other object B into AI. On the other hand, if you first take a direct sum and then do the Yoneda embedding, you end up with this. This is, of course, bigger than this, because this allows you to have an infinite number of sort of components. This doesn't. Classical example, take this object B to be another direct sum, another copy of this. So now take this direct sum. This exists in A. This is perfectly good object of A. So plug this into this representable module. Then the identity morphism of this direct sum is not an object here, because it's an infinite sum of identity morphisms of each AI, but it's a perfectly good identity morphism here. So and if Yoneda embedding does not commute with infinite direct sums, then you get a question: should you be really taking this direct sum in mod A, or if it already exists in A, maybe you should be taking it in A. So if you take this direct sum, if you assign to collection of objects AI this direct sum, performing the operations here, that's what gives you definition of an absolute twisted complex. But in this situation, you assign to a collection of objects an a priori non-representable module. So your convolution is only ever mod A sort of valued. It has no chance of filtering through the unit embedding of A in mod A, which is a shame given that A is sort of grossly huge. It already has all the shifts, sort of direct sums, all the complexes of vector spaces sitting in there. If you assign to any collection of objects AI this direct sum taken in A, then you get a different category. Let me denote it for a moment TW plus minus A of A. So in it, essentially it's the same definition as you saw here, only instead of this finiteness condition, we now allow infinite number of twisted differentials out of any AI, out of the same AI. But as long as the total sum of differentials still defines an endomorphism of this direct sum of shifted copies of AI. Now, when building a convolution functor, we assign to AI now a representable module, home from AI into this direct sum. The convolution functor filters the unit embedding of A into mod A. And what does it mean that it filters? It actually means that you have a convolution functor going from unbounded twisted complexes over A into A itself. And then the formal standard convolution functor we saw before is just a composition of it with A to mod A. Now, this is true because our A is mod C. This happens not just because you've got all direct sums and you're clever and you've taken a representable module. After you assign to this representable module, you must be able to modify it, the natural differential in this module, by this. And in order to modify this and to still get an object, you have a representable module, you modify the differential. You're allowed to do this, but you will get a non-representable module. However, if for any possible choice of a new differential on this, you still get a representable module, then this happens. So this is a very special property of A equals mod C. It's closed under twisting, under changing a differential in any of its objects. So once you have this, you're in a really good position because you can dispense dealing with mod A altogether. You can straight away define your convolution functor to be this. You never touch mod A, so you can allow your A to be a large category and just forget about set theoretic issues altogether. So, but what do you do if your A is not some category of modules? Well, there is a following useful lemma. Let B be a DG category, which admits countable direct sums and shifts. This is a really mild condition. Many small categories can do that. The following are equivalent. Your category is closed under twisting. This means that if you have any object B, any degree 1 morphism F from B to B, with condition that dF plus F squared, compare this with d alpha ij plus alpha jk alpha ij, and you will see that this is just this in the case of sort of one object. So this is really twisted complex condition for a single object complex. So for any object F like this, if you take a representable module defined by B and modify the natural differential on it by F, what you will get will still be represented by some object of B. So in a sense, B admits convolutions of a single object twisted complexes with one single differential F going from a complex from B to itself. So this is actually equivalent then to B admitting convolutions of all unbounded twisted complexes. So this is equivalent to any twisted complex in the sense of sort of in this sense, where we take direct sums in B itself. This convolution functor then filters through Yoneda and gives you a convolution functor back into B. And third condition is simply, never mind convolutions. Just look at the Yoneda embedding of B into its own category of twisted complexes. This is an equivalence. So if you've got the point, somehow we arrived at the end of thinking about all this, because originally we were motivated by this situation. When we already have all things we need in our category, we didn't want to step up to a bigger universe. We just wanted to sort of sit here. But towards the end of this talk, I will hope to convince you that this formalism, which I will introduce now in our final definition of unbounded twisted complexes, is really necessary. There will be a situation where this is not just a mod A. So let A be a DG category, which admits a fully faithful embedding into a DG category B, which has countable direct sums, shifts, and admits is closed under twisting. Then unbounded twisted complex over A relative to B, and that's the reason for the term absolute. Absolute means sort of relative to mod A, sort of relative to the envelope of A, which always exists. Well, Z-graded collection of objects of A, twisted differentials going from every object to every object. And now, if in here we said, in absolute case, we defined, let's have this finiteness condition. Oh, by the way, it's equivalent to the sum of differentials defining an endomorphism of the direct sum. Here we simply use that as a definition. The sum of the twisted differentials must define an endomorphism in B of the direct sum of AI shifted by minus I, and the same old twisted complex condition. You define then a DG category of twisted complexes relative to B of A. Now you simply say tautologically, this home complex is just this home complex. In effect, you can still say that this is any collection of Fij morphisms from AI to Bj of a prescribed degree, as long as but there is a condition on this collection. The result, this collection must define morphism of graded modules here. And the natural differential on this, if you translate it to sort of something to just looking, when you look at this collection, this is a collection of data in A. So if you don't want to be dealing with B, the differential is given intrinsically in A by the same formula. So same formula where we same formula where to differentiate a component from AI to Bj, you differentiate it and then you compose it with all twisted differentials, pre-compose it and post-compose it up to signs. Exactly the same formula will compute you intrinsically in A in terms of this data. Something that via graded space graded vector space isomorphism will correspond to a differential in B here. And sort of the end result is that you've got your convolution functor. You can convolve any unbounded complex of any unbounded twisted complex over A relative to B straight to B itself by convolving this collection to this direct sum with the change of differential. Now, before I proceed to a third part of my talk, which is to give an example which sort of motivated us to look into this and to show a situation where you really have a non-trivial B here, which is not mod A, and not A itself. So far we've seen two cases, mod A or A itself if A is already mod C. But are there really any sort of interesting cases where this doesn't happen. Before I proceed to that, are there any questions so far? Cool. Can somebody confirm that Zoom is still alive?
Perfect. Everything's good.
Thank you. Thank you. So here is the original application which we had in mind. I mean, the reason we came into sort of all of this. So we were writing a paper which then became two papers, and the paper on unbounded twisted complexes became a third paper in the package. So what we were after is a notion of A-infinity structures in monoidal DG categories. So suppose you have a monoidal DG category. I mean, my favorite example, of course, is mod K. That's everybody's favorite example. Category of complexes of vector spaces, where you have a perfectly well-defined operation of tensoring to complexes. However, a more interesting example is if you have a small DG category and you take all DG functors, DG endofunctors from C to C. But even better, suppose you take all enhanced functors. Suppose C is a sort of, suppose you take all enhanced functors from C to C. Now, this is a whole subject for a whole different talk, but any small DG category can be considered as a Morita enhancement for the triangulated category, which is its category of its compact derived category of the compact modules over C. Roughly, what you end up doing is you take C, you Vion it embedded into mod C, you take the triangulated hull on the homotopy level of C. So you throw in all the iterated columns of objects of C. And then you also throw all the homotopy direct summons. What you get is this. So this DG category is sort of, it's Morita because the older notion of DG enhancements said that C had to be a special kind of category, pre-triangulated category, category quasi-equivalent to its own pre-triangulated hull. And then the homotopy category of C would be the triangulated category that enhanced it. It's really much simpler to allow any small DG category and view the triangulated category which underlies this enhanced category to be this compact derived category of modules. And then enhanced functors from C to C is simply, I mean, a certain kind of CC bimodules, which then define sort of exact functors from DC, from the triangulated category to triangulated category. So the moment when you have a category of endofunctors, you can have a monad. You can have a sort of functorial algebra in there. So in your monoidal category, what is an algebra object up to homotopy? Because if we want to enhance a monad over this triangulated category, then anything that is an algebra in here will only lift to algebra up to homotopy in the enhancement. So this is the motivation behind that question, but you can ask this question in any monoidal DG category. So what I'm asking for really is, I mean, the first step is what is an algebra object not up to homotopy? Well, you take an object A in A, you have a multiplication operation, A tensor A into A, and then you want the square to commute. There's also unitality condition, but I mean, unitality is a whole separate story, and let me not touch it for the moment. Unitality is, in a sense, a condition and not data, surprisingly enough. So, so A defines an algebra object in H0A if this commutes. What is the right? I mean, but the moment you allow this to commute only up to a homotopy, then you need a coherence condition on interaction of this new piece of data you introduced with your operation M. So this is very well known in one specific case when A is your category of complexes of vector spaces. Then we have a perfectly good notion of A-infinity algebra, strong homotopy associative algebra. So given a complex of vector spaces and higher operations on it, where Mi is operation from ith tensor power of A into A of degree 2 minus I. So when I is 2, you get a degree 0 operation, your multiplication. Then this set of data defines an A-infinity algebra. If, well, the original definition gave you this condition. It simply gave you a hard sort of bunch of explicit equalities. For every I, and for you must take a sum of all decompositions of I into j, k, and l. And the best way to think about this is you have AI, and then you break this up into AJ tensor, AK tensor, AL, and then you apply MK operation to this, and then you apply this, convolves this to a single copy of A, and then you apply the corresponding higher operation to the rest. You get a bunch of operations from A to the power j plus k plus l to A itself, and you want the sum to be 0. Note that this makes use of M1. M1 is internal differential in mod K. Any complex of vector spaces has internal differential. So this is a bit rubbish because in this situation, we don't really have an internal differential on A. Now, a point of view which was well understood for a long time is that actually where do these equalities come from? Well, consider a non-augmented tensor algebra. Non-augmented tensor algebra just means I don't sort of adjoin a copy of monoidal unit. I just take a direct sum of all tensor powers of A starting from the first shifted by minus I. So this is a free tensor algebra on A shifted by 1. And my operations are this degree condition is precisely such that I obtain a sort of degree 1 morphism from this tensor algebra to A itself. And universal property of sort of then ensures that any morphism like this defines me a morphism like this from the, I think I should say, coalgebra to itself. So sorry, this is not sort of tensor algebra, this is tensor coalgebra, of course. But the point is that you lift this morphism to this to this structure. And then this uniquely determined lifting must define you a new differential on the underlying sort of graded space. So on underlying graded coalgebra. But hold on, haven't we seen this story somewhere before? We take this object, the direct sum of now AI's shifted by minus I. We take the natural differential that exists there. We take the differential, we take some modifying information, and we ask for the condition that this is a new differential. This sounds like there's a twisted complex behind it. And of course there is. And this is how to do this, the A-infinity algebra story in any monoidal DG category, without trying to embed it into mod A. I mean, the beauty of the original definition of twisted complexes is that essentially it gave you a set of data intrinsic in A, the conditions intrinsic in A, the differential on morphism determined in A, which ensure that right things happened after the unit embedding. So similarly here, if you have a monoidal DG category, if you have an object in it, and if you have a collection of higher operations from AI to A of degree 2 minus I, then this collection is an A-infinity algebra in A. If the following thing is a bounded above twisted complex relative to some B, you can always take mod A, but you don't have to. This is called a non-augmented bar construction, and if you've seen one bar construction, you've seen them all. So we've got M2 from A2 to A, and then we then apply sort of M2 successively in all possible ways to extend M2 sort of further back up the complex. complex. We have an M3 going from A3 to A, and then to define a twisted differential from A4 to A2, you apply M3 in every possible way. From A5 to A3, apply M3 in every possible way, and so on and so on. So this gives you a well-defined notion of A-infinity algebra. And in exactly the same way we define A-infinity modules, um, which we call node infinity A, and infinity bimodules. I mean, for modules, you really want to be working not in a monoidal DG category, but a monoidal bi category. So you can have endomorphisms of an object being algebras acting then on home spaces from that object into different home categories from that object into different guys. So the last remark I would like to make is I promised you an example of non-trivial B. Well, when defining A-infinity modules, when defining A-infinity bimodules, you always take your bar construction just relative to mod A. But the moment you get comfortable with the notion of A-infinity module over A, so some collection of objects sort of Fi and morphisms from A sort of tensor E, AI into E. These are your structure morphisms, which then, similar to algebra, you will get your object E being a module over A in the homotopy category. But the moment you are comfortable with this, you go, wait a moment. I now want to be taking cones of this, and eventually I want to be taking twisted complexes of this. So when you start working with twisted complexes of A-infinity modules over your A, then you have a fully faithful embedding. A-infinity complex, A modules in A. So in order to get this theory off the ground, you'll have your A category A is embedded into some category B where we can take cones. Usually this is mod A, unless there is a good reason for it to be something else. And this is where you take all the shifts. This is where you take all direct sums and so on. But observe that anything that's an A-infinity module over A in A is automatically an A-infinity module over A in this bigger category. In fact, we can consider A-infinity modules over our algebra A in B, because algebra A lives here and it's just as good an A-infinity algebra here. So when defining twisted complexes of A-infinity modules, you do not want to take an absolute notion. You don't need to go from this to a horrible big category mod node infinity A. That's awful. You're going one cardinality up and adding a lot of junk. What you need to consider twisted complexes of A-infinity modules over A relative to this embedding. This is your big category. This is where you take all the direct sums and shifts. This is where twisting by differential exists. And so this kind of is what you want to be using. You view A as which is an object of category A and with an algebra structure, as an algebra structure in category of modules via unit embedding, and you sort of deal with the infinity modules over this. You do not first take all infinity modules over your object A in A, and then take all DG modules over there. That is gross and really quite terrible. So here's your example. When forming unbounded twisted complexes of A-infinity modules, we do not take this itself. This can be very small and not have shifts or direct sums. We do not take the category module of modules over it. That's grossly huge. We take a natural category, which in a sense lies in between the two, which is this, which is much more natural category for all this game to exist. So that's my story. I hope I've given some motivation to work in a full formality of twisted complexes relative to sum B, which is neither A nor mod A. Are there any questions?
Thanks very much. Timothy, for the very nice talk. Yeah, so if there are any questions, then just unmute yourself and ask. I had a
Could you please,
question.
sorry,
Go ahead. Go ahead.
could you please say again what not infinity A is?
So node infinity A, these are A infinity modules over A.
I
So
see.
here
Oh,
here I made a definition of A infinity algebra.
right.
Once you have an A infinity algebra, you can consider modules over it.
Hmm.
They work in exactly the same way, only you replace here you have A, here you have A E, here
Hmm.
you have A squared E, and here you have your original action AE onto A into E. Here you have the higher actions, and then you have the full bar complex. The bar complex needs to be a twisted complex in order for this to be an infinity module.
Hmm.
So basically, this complex is really just the bar construction. It is the right condition you need to impose on this higher operation for them to define your infinity algebra or infinity module. But when you have modules over something, you want to work with twisted complexes over that.
Hmm.
So the moment you have your monoidal DG category, in our example, we actually didn't need an A infinity algebra. We
Hmm.
had an ordinary algebra, but we needed modules up to homotopy over that algebra. The moment you're doing that, you have no choice. You cannot just deal with modules up to homotopy. They do not form a nice category. You have to take a full category of A infinity modules over your algebra. But then when you want to work with sort of twisted complexes over that, then you need to ask yourself, where do I take the direct sums? Same
Hmm.
old question. And the answer is you do not want to be taking direct sums into category of modules over this. This is grossly huge.
Hmm.
Rather, you want to take your algebra, embed it into nice category mod A, which has all the shifts via Yoneda,
Hmm.
and then considering it as an algebra objects in here, take all A infinity modules over that. So A infinity modules over the same algebra, but in your bigger category. This will include all these guys, allow you to take shifts and direct sums, and it's just much more natural category
Hmm.
to be taking direct sums and sort of convolutions of your twisted complexes in. So I hope I answered your question to
Hmm.
some extent.
No, that was actually very helpful.
Yeah, I wanted to ask the same question. Just another question. Do you have any geometric examples where this machinery might be very useful to apply?
Well, yes, actually, but this is really a subject. This is really a subject for
For
another
another talk.
talk.
Yeah.
But I'll answer very quickly.
Okay.
The reason we are doing why would anybody want an enhanced monad? Because essentially we want to get to bar back,
Hmm.
meaning that we want to have a monadicity theorem for enhanced triangulated categories, not for there is bar back Lurie.
Hmm.
But Barback Lurie, the moment you step into infinity category world, you've got all the coherency data you ever need to perform abstract constructions, which become almost tautological, because if you assume you have all the data you need, then things like monadicity theorem work out of the box. But then somebody asks you an embarrassing question, sort of what happens on P2? And it's pretty difficult to compute that. So we hope for our theory to allow when we eventually release the last paper in this sequel of papers, we hope to have an explicit bar back, and therefore things like given an algebraic variety X and an affine cover of X, we want an explicit description of how objects in derived category of X can be glued from objects of derived category on here plus extra data, and this data is essentially data of A infinity co-module over certain sort of very explicit algebra. So explicit descent for derived categories. And you can also do crazy things like closed descent, so fake descent. So if you have X and Z closed subvariety here, you can play the same monad game, and you can describe in terms of certain extra structure on DZ the formal the derived category of objects in X supported on Z,
Mm.
which is the formal neighborhood of Z and X. And it turns out that if in some nice situations, so this turns out to be basically things in here with the structure of a module over infinity module over essentially wedge algebra of the normal bundle. If so-called sort of in the simple cases where this can be, for example, split, this can be split. So there's in this case, the sort of the first formal neighborhood actually determines the whole thing. But if in general case, you need to take this algebra, but now with certain extra operations, higher operations, which encode the data of the sort of full formal neighborhood. And then you'll be able to, again, describe this in terms of objects here with an extra data of module over this algebra. But this is sort of very much work in progress, and at the moment, sort of I'm waving my hands. But let me stress, the difference between this and infinity categorical versions of this is that we hope to be able to present this in terms of very explicit data that you can really sort of apply to P1, P2, any algebraic variety and get a concrete answer. So I hope that.
Yeah, thanks. This looks very interesting.
Maybe when you're at the MPI, and then we can hear a next talk.
Yeah.
Indeed. So,
do we have any other questions from the audience? Or look
I also had a brief question. So if you have two DG categories which are Morita equivalent, so their bounded twisted complexes are I don't know, quasi-equivalent. Do you then expect that these unbounded twisted complexes are also equivalent?
Two categories which are Morita equivalent. Yes, of course. I don't know. I think it's pretty. I mean, wait.
Yeah, is it clear or is it?
Sorry. This is a subtle question. This is a lot subtler question than it seems. We in the big preprint called Infinity sort of. Let me not try to answer it on the spot. I will think about it. Can I ask who is asking the question?
Severin.
Severin, right. So if can you please email me about this, because I don't I don't want to give a wrong answer now. I will give a much better answer once I have a chance of sort of think about it for 10-15 minutes.
Okay, sure.
So there is a subtlety involved, because Morita up to Morita equivalence, of course, determines fully sort of compact derived category.
Exactly.
Yeah. But beyond that, it's the answer should be something like, yes, if you can somehow figure out, so suppose you have A and A dash, right? So the problem is you need to figure out relative to what to take sort of, if you take absolute complexes, I don't think there's a chance of showing that. But if you can somehow take the twisted complex relative to the same category, then it might be possible. Then it might be possible to do this. But as I said, let me not give you a wrong answer by sort of by giving you sort of unthought about answer. Let me think about this and email you about this.
Okay, great. Thank you.